What's up guys, it's Sean here from The Computer Scientist. Today we will be enhancing the original experience replay technique to prioritized experience replay. Now as a refresher, recall that our agent interacting with the environment is trained each time step using the current state, its action to take in that state, the resulting next state, reward, and whether that action terminated the episode. Then with the original experience replay technique, we have a fixed length buffer where we store each time step's experience tuple so that we can randomly sample a batch of tuples to train the agent at the same time. Experience replay alone speeds up training significantly, but there is one main improvement that we can make, and this has got to do with how we sample experiences to train from the buffer. In experience replay, we are only sampling experiences randomly from the buffer. But what if we could learn more from some experiences than from others? For example, this could be a state in the environment that occurs in rare cases, or perhaps a bad action that caused the episode to terminate. In order to select these experiences to train more often, we can assign priorities to each experience tuple in the buffer, representing the learning value of each tuple. This is the idea behind prioritized experience replay, as outlined in the official research paper, which I'll link in the description. But how do we know how much to prioritize each experience tuple? Let's consider an example where you're studying for a quiz tomorrow and have some practice problem sets to prepare for it. So you go through and finish the first problem set, and after marking your answers, your results look like this. Dang, I could have sworn 1 divided by 1 is 3. Now you only have tonight to study, so which problems do you start with? Probably the ones where you made the most errors. Now if we relate this to reinforcement learning, we are training our agent to minimize the error which we approximate as the difference between the predicted Q value for the state action pair and the Q target value calculated from the Bellman equation. So we can actually set our priority value for each tuple to be directly proportional to the absolute value of this calculated error. There's just one small issue here, that is when the error turns out to be 0. We don't want our priority weight to be 0, as this experience might be useful later on. So we'll add a small offset value to each priority to fix this. Now when we sample experience, we can convert these priority weights for each tuple to a probability of choosing that tuple for the current batch. The simplest way to do this is to divide each priority value by the total sum of all priority weights. But since our priorities come from the error which depends on the approximated Q target value, the priority could have approximation errors which could cause some priorities to be too high or too low. To address this, we can dampen each priority weight towards 1 by raising it to the power of a priority scaling constant A, which is between 0 and 1, where A equals 1 results in full priority sampling and A equals 0 becomes pure random sampling of normal experience replay. Okay, so now we've taken care of the sampling of experience according to the priorities, as well as setting the priorities of each sampled batch of experience tuples, but we just have one more adjustment to make. Because we are now sampling experience non-uniformly, this will create some bias in our neural network towards those experiences that have a higher priority. To understand why, let's look at how we update the Q network for each state action pair. So for any optimization problem, we first need to define a loss function that we want to minimize, which in our case is the squared error. Then for each layer in the Q network, we update the weights and biases, which are represented as theta, towards the negative gradient of the loss function, and we weight that by a small learning rate alpha. And ideally, we would do this step for every state action pair that the environment gives us. And with experience replay, we are approximating the environment with a replay buffer and accelerating the training by sampling a batch of experience to train on. And because we sample randomly, the original distribution of experiences that the environment would produce is preserved. However, once we introduce sampling priorities to the replay buffer, then this changes the distribution in favor of the higher prioritized experiences, making the network anticipate these experiences more and overfit them. So to address this, we need to scale down the update step by a weighting factor according to the probability they were sampled with. So with our priority and sampling probability that we defined here, the value of this weight factor is 1 divided by the total replay buffer size times 1 divided by the probability. This will reduce the step size for higher probability experiences and therefore avoid excessive update steps from the increased frequency of training on those experiences. Now, since the bias correction is more important later during training, we can introduce an exponent b that starts off as a low value and increases to 1 over time. And that's our final weighting factor, and in the paper this is referred to as important sampling weights, which we need to add to the network update step to complete the prioritized replay algorithm. So now we're ready to code this up. So I'm back in our Google Colab notebook from last video, which is essentially just Jupyter Notebooks on Google Drive. And we'll start by introducing priorities to the replay buffer class, so we will define a separate dequeue for holding the priorities so that it doesn't interfere with the existing buffer implementation. Then when we add an experience tuple, we also want to add an initial priority value. So since this is a new experience, it's fairly important to train on, so we will save its priority as the maximum priority in the buffer, so that it has a high chance of being selected in the next batch. Then when we are sampling experiences, we first need to convert our priorities into sampling probabilities, so I'll create a function getProbabilities that takes in the priority scale value A that dampens the priorities. So we first get our scaled priorities by raising each priority value to the priority scale, and then our sample probabilities from dividing each scaled priority by the sum of all scaled priorities. We can pass these probabilities as sampling weights to the random.choices function, but instead of sampling the experiences directly, we will sample indices which we will use to retrieve the experiences and the corresponding probabilities for calculating the importance sampling weights. Then we can retrieve the batch of samples from the buffer by indexing it with the list of sampling indices. We will also need to calculate the importance sampling weights from the corresponding batch of probabilities, so I'll create another function for that which takes in the sampled probabilities. This will just apply the equation of 1 over the buffer length times 1 over the probabilities. We should also normalize the importance weights to be between 0 and 1 to keep the update step size bounded. We can then retrieve the importance sampling weights from the probabilities at the sampled indices and return these after the tuple of experience lists. Then in our agent's train function, we need to adjust for this change by treating the replay buffer's output as a tuple, with the first item being the tuple of experience lists and the second being the importance weights. We then need a way to pass the importance weights to our queue network to adjust the update step. So going to our queue network class, we will create another placeholder to hold the importance weights. Then, since we also need the error output to save as our priorities, we will move it from the loss function to its own variable. This makes it easy to incorporate the importance weights to scale down the loss function's value by multiplying it with the squared error, which will in turn scale the resulting gradients. Then, in our update model function, we want to add a parameter for the importance weights to pass into the feed dictionary. We can also have this function return the corresponding error values for each sample by running the error operation and unpacking it from the output. Now we can go back to the train function to pass in the importance weights and then save the returned errors. And we can actually use the epsilon value for the exponent b, where we use the complement to start with a low b value that increases as epsilon decreases during training. Finally, we just need to use the returned errors to set the new priorities of the recently trained batch. So we will create a function setPriorities in the replay buffer that takes in a list of indices to update and the error values for calculating the priorities. Then we will just loop through each pair of index and error and set the priority value at that index to the absolute value of the error, plus an offset value which we can default as 0.1. Now when we call this function, we need a way to pass in the sample indices, so we can just return them from the sample function, unpack them, and then just pass them in with the errors. And that completes our prioritized replay algorithm, so we can rename this to suit. Let's also increase the maximum buffer length to 100,000 to store more experiences so that it better represents the environment. And now let's compare the performance of prioritized replay to the regular experience replay using our trial run loop. So when we call our agent's train function, instead of alternating between double DQN, we want to vary the priority scale to incorporate the priorities. So we can pass in the priority scale as a parameter A that we would then pass to the sample function. Now the research paper suggests that 0.7 is a good value for A, so we can just alternate between this value and 0. So then after running the trials and fast forwarding to the results, we can see the difference between the two approaches using some basic hyperparameters. And it seems that on most trials with prioritized replay, the agent's average score increased slightly faster over fewer episodes of training than with the original experience replay. But of course, prioritized replay could be more effective for some environments like Mountain Car, where the goal is much less easy to come across during exploration. So you just learned how to extend experience replay to prioritized experience replay. And as you noticed, there are heaps more hyperparameters with this extension that can be tweaked for better results. So I definitely encourage you to play around with those and post in the comments what you find worked best. Anyways, thanks so much for watching this video. If you found it helpful, be sure to give it a like. And if you're new to the channel, subscribe for more DIY reinforcement learning tutorials. But until next time, keep learning like a machine. Bye!